One of the fundamental controls on Earth's climate is the balance of incoming solar radiation that reaches Earth and the energy that flows back from Earth into space. And this balance is referred to as Earth's energy budget. In this tutorial, we'll talk about components of Earth's energy budget and how changes to the energy balance can have large impacts on the state of Earth's climate. The amount of incoming solar radiation that reaches Earth's surface varies with latitude. The incoming solar radiation at the equator is more direct than at the poles, and this results in a large-scale difference in the distribution of incoming solar radiation, as seen in the map on the right, with more energy at the equator and less at higher latitudes. However, the amount of incoming solar radiation isn't the only component of Earth's energy budget. We also have to consider the emitted radiation from Earth's surface. The graph on the left is showing the average incoming solar radiation with latitude in red, which highlights what we saw in the previous slide, with increased incoming energy at the equator and less incoming radiation at the poles. Now, this blue line is showing the outgoing radiation that's emitted from Earth's surface. At the equator, there's more incoming than outgoing radiation, which results in a surplus of energy. At the poles, there's more outgoing radiation than incoming radiation, resulting in a deficit of energy. And this uneven distribution of net energy is closely related to surface temperature. The map on the right is showing the annual average surface temperature. And you'll notice that at the equator it's warmer, whereas at the poles it's cooler. In later tutorials, we'll talk about how some of this energy at the equator is distributed globally. So Earth's energy budget is a bit more complicated than just looking at the incoming versus outgoing radiation, because not all of the incoming radiation actually reaches Earth's surface, and not all of the emitted radiation actually leaves Earth's atmosphere. This is a diagram showing the incoming solar radiation and outgoing radiation, and what happens to these incoming and outgoing radiations along the way. Starting out with the incoming solar radiation. Only about 47% of this radiation actually reaches Earth's surface. About 7% is scattered to space, about 17% is reflected by clouds, and about 6% is reflected by the surface. 23% gets absorbed by air, clouds, water vapor, ozone, dust, etc. in the atmosphere. Moving to the right, we can take a look at the outgoing long-wave radiation. Energy and radiation is released from Earth's surface through convection, evaporation, and long-wave radiation. However, about 6% of this outgoing long-wave radiation gets absorbed by clouds, CO2, water vapor, etc. in the atmosphere. Changes to Earth's system, either through natural phenomena or anthropogenic activities, can create an imbalance in Earth's energy budget. And this last component that we just talked about, that percentage of outgoing radiation that's absorbed in the atmosphere, is really important, especially today. The process by which the 6% of outgoing radiation that is absorbed by the atmosphere is known as the greenhouse effect. This is a naturally occurring process, but changes in the concentration of atmospheric greenhouse gases affect the amount of radiation that's absorbed by the atmosphere. In a stable and balanced system, the incoming solar radiation is balanced by the outgoing energy. However, in an imbalanced system, there's more incoming solar radiation that gets trapped than is being released. And a main reason for this is the influence of increased greenhouse gases in the atmosphere due to anthropogenic forcings. An increase in atmospheric greenhouse gases would result in more of that outgoing radiation being trapped, resulting in warming. To assess global variations in climate variables, such as temperature and incoming solar radiation, it's useful to be able to extract and compare spatial and temporal subsets of data from a larger data set. For example, comparing global temperature data from 100 years ago to global temperature data from today can help to assess anthropogenic impacts on Earth's climate. In this tutorial, we'll explore multiple computational tools in X-ray that allow us to select and compare data from a specific spatial and temporal range.